Hello everyone, welcome to NPTEL online certification course on Introduction to Application of AI to Robotics. Today we are going to talk about acceleration of a rigid body. So before we move on to the dynamic equations of a manipulator, this is the topic which I would like to discuss with you and where we would like to see how the linear and angular acceleration of a rigid body can be defined, okay, and how we can get the expression of linear and angular acceleration of a rigid body. So, the learning objective for this lecture, I expect from all of you that by the end of lecture you will be able to learn the acceleration of a vector in a translating and rotating frame, what the inertia tensor is, as well as the parallel axis theorem which we mostly use to find out the moment of inertia at any axis which is parallel to the the center of mass axis. Okay. So, the content for this course are initially we are going to see the linear acceleration of a rigid body, then we are going to see the angular acceleration of a rigid body, then we are going to see the mass distribution, okay, and from that mass distribution we are going to see the inertia tensor for a rigid body. Then we will be talking about the center of mass and then the parallel axis theorem and mass distribution in robot design, and how do we specify the mass and inertia for AI in the URDF file. So, this is what we are going to see. Okay. So, what is a rigid body? Okay. So, we have seen this definition earlier also, but I thought that since the discussion is about the rigid body here, so let us have a definition of the rigid body. Okay. So, see, for any rigid body, the distance between the 2 points that is always constant. Okay. So, regardless of whatever the external forces act on that rigid body, and in robotics we consider say arm of the robot or say legs of a legged robot or joints, they are modeled as rigid bodies connected at joints. Okay. So, robot links are modeled as rigid bodies connected at joints, and as I said, various parts such as arms of the robot, a manipulator if you are talking about, if I am talking about a say quadruped robot, then the legs of the robot, all these are considered as rigid, and that makes our life much simpler in the sense that the treatment is much easier. Okay. Next associated with rigid body, next important term is the degrees of freedom. We have seen the definition of degrees of freedom, okay, earlier, which is the number of coordinates required to specify the position and orientation of a rigid body. Okay. So, for a rigid body, essentially we require 3 translational displacement coordinate x, y, z, and 3 the rotational coordinate, okay, that is roll, pitch and yaw. So, together they constitute the 6 degrees of freedom in a rigid body. Now, when we are talking about dynamics of a manipulator, essentially there are 2 types of problem which we come across in a manipulator dynamics. Okay. So, the first one is that say for a given trajectory point, okay, so for a given trajectory point, that is I am given say the joint position, the joint velocities and the joint acceleration. So, these are the vectors. Okay. So, if I am given these values and I am asked to find out what my joint torques are going to be. Okay. So, this is the one problem, and this problem we use for controlling of a manipulator. Okay. And this problem is also called as the inverse dynamics problem. That is, for the given joint position, velocity and acceleration, our intention is to calculate the joint torque. Okay. Now, the reverse of this is another problem where we know the joint torque and our aim is to find out these three, say, vectors, that is theta, theta dot and theta double dot, alright. So, this problem is what we call it as the forward dynamics problem, and its purpose is naturally, since I am interested in finding the joint velocities, joint position, joint acceleration. So, naturally I want to visualize it, that is I want to go for simulating the robot, okay, that is for the given joint torque, how much my joint rotating, what joint velocities they have, what joint acceleration they have, okay. So, before we move further, let us see some conceptual definitions, acceleration of a rigid body, okay. So, the linear and angular acceleration of a rigid body can be defined as, say, if I am taking a vector q on the rigid body, okay, and say there is, and that is vector is defined with respect to frame B on the rigid body, okay. So, the acceleration of the point can be given as time derivative of this v, and this is nothing but velocity at t plus delta t minus the velocity at t divided by delta t with the limit delta t tending to 0. Okay, so this is for the translational acceleration. Similarly, I can define the angular acceleration. Okay, so this way my angular acceleration can be defined here. Okay, and if the reference frame of the differentiation is understood to be some universal reference frame, then that is this one, it's a universal differentiation is done in a universal reference frame, then we go for a short notation, okay, and we just represent the velocity this way and the translational acceleration, and similarly I represent the angular acceleration this way. Okay. Next, let us look at the linear acceleration. Okay. So, suppose we have a vector qb, okay. So, there is a vector qb, alright, q with superscript b indicating that the vector is defined in frame B, okay, and there is another frame A, okay, and the B has got an angular velocity omega with respect to frame A, okay. So, this is given by this velocity vector. So, here we have the origin of both the frames, that is the B and A, they are same, they are coincident. Then, so what, as we have seen in the previous lectures, I can write the velocity of q expressed in terms of frame A as velocity of q expressed in terms of B, and you see we need to have everything represented in terms of the same frame. So, since this is there in the term of frame A, so I need to carry out a transformation here, a rotation matrix here from B to A. Okay. So, this is there, plus we are going to have an omega cross r term over here because the frame B is rotating with respect to frame A. So, this is your omega B cross A, B expressed in terms of A cross this your vector qb, and again this vector qb has also to be expressed in terms of frame A as here. So, I multiply this with a rotation matrix R B to A. Okay, fine. Now, let us write this expression into another form. Okay. So, this is velocity of vector q expressed in terms of frame A. So, this I can write as d by dt, right. This is qb r b to A, and then we are going to have the same term as over here, alright. Okay. Now, let us take the derivative of both the sides of this equation. Okay. So, what we are going to have? So, VQA derivative here, we are going to have d by dt of this term, okay, plus we are going to have derivative of this term cross the same term over here, plus we are going to have this term, okay, cross derivative of this term. So, here basically used the derivative of the two multiplications. Alright. So, this is what we have done over here. Now, I can further simplify this. So, this is VQA derivative. So, this is what basically now what I can do is that here we had this vector q, okay. So, if in place of q, if I have got this velocity vector, okay, then what I can write over here, okay. So, if I have got this velocity vector, then I can write this as V, then I can write here this is the derivative of this one. So, I am going to have this VQB or B2A this plus I have omega cross this term. So, I will have omega cross this term itself over here, okay. Plus then we have the same term over here plus this omega BA plus I am now expanding this one and writing it over here from this equation. Alright. Okay. So, next I can further simplify this. So, this is the first term remain as it is, and then I can have this BA omega B expressed in terms of frame A, this velocity term. So, we are going to have some two such terms actually, okay. So, one is this term and another is this term, okay. So, I am going to get two such terms. So, it is 2 cross this one plus the same term over here plus I am going to have this omega BA here cross this term omega BA cross QB or B2A, okay. So, this way I can get the acceleration of vector q expressed in terms of frame A, okay. So, to generalize the case in which the origin are not coincident. So, this case we did some simplification, okay. Here we assumed that the origin of B and A, they are lying at the same point, but here we say that origin of B and A, they are not lying at the same point, rather they have got some velocity. So, I can add this additional acceleration term, that is the acceleration of B origin expressed in terms of with respect to frame A and expressed in terms of frame A, and say this one plus rest of the terms as it is. So, this is my general expression, and this equation can be directly used for a prismatic joint, okay. Fine. Now, if my QB is constant, okay, this QB is constant, this is not changing, okay. So, what does this means? It means that basically this velocity as well as acceleration, these velocities terms are 0. So, if I substitute these two in this equation, I can simplify this equation further. So, this term goes to 0 and this term also goes to 0. So, I have got this term, I am left with this term, okay, plus I am left with the other term, okay, and this expression can be used for finding out the acceleration, okay, in case of the rotational joint, acceleration of a point in case of rotational joint, okay. So, that was all about linear acceleration. Now, let us see what happens to the angular acceleration, okay. So, to do that, suppose I have got 3 frames, okay, a frame A frame B and a frame C, and their origins are coinciding. Frame B has got velocity with respect to frame A omega, and frame C has got velocity with respect to frame B, okay. So, I can write this as I can express the velocity of C with respect to A as velocity of B with respect to A plus velocity of C with respect to B, and of course, everything expressed in terms of frame A, alright. So, this is what we can do, and by differentiating then I can get the acceleration term, okay. So, if I differentiate this, so this differentiation and this differentiation and this differentiation, so this is d by dt of this complete vector, and again this derivative of this vector I can write the general expression for that. So, it is this vector derivative plus omega cross this vector itself. Okay. So, omega b cross a cross this vector itself. Okay. So, this way I can evaluate the angular acceleration. We are going to use these concepts in our next lecture when we are going to see how the Newton-Euler equation works. Okay. Next, let us see the mass distribution. Okay. So, suppose you have got a rigid body, and on this rigid body I have got a small element of volume dV, okay, over here, and say this is my frame A over here, and from origin of this frame, this location of this elemental volume is given by PA. Okay. So, a small a basically tells that it is with respect to frame A, okay, origin of frame A. So, for a single degree of freedom translatory motion, we talk about mass of a rigid body, okay. But in case of rotational motion about a single axis, we talk about the moment of inertia, okay. In the case of rotation about an arbitrary axis, we need a complete way of characterizing how the mass is distributed in the rigid body, okay, and that is done using an inertia tensor. Okay. So, inertia tensor is defined with respect to frame A as IA, and these it is a 3 by 3 matrix basically, okay, and the diagonal terms are here Ixx, Iyy, Izz, that is the moment of inertia about x axis, and then you have the cross coupled terms, other off diagonal terms are there. Okay. So, here the scalar elements, this is how they are defined. So, Ixx is defined as y square plus z square here into the mass, okay, mass of the element, and that is given by the density time the elemental volume, and I carry out a volume integral over here. Okay. Similarly, I can define for the moment of inertia about y axis and the moment of inertia about z axis, and these terms are called mass moment of inertia. Okay. Other terms, off diagonal terms, that is Ixy, these are defined like this, xy cross the elemental mass which is rho dV. Similarly, Iz and Iyz are defined, and these are called mass product of inertia. Okay. Fine. Okay. Here each elemental volume is located by this vector, okay, that is xyz transpose. So, these set of 6 independent quantities will for a given body depend on the position and orientation of the frame in which they are defined. Why I am talking about 6 independent? Because here we have the 6, the 3 diagonal term, and then we have 3 off diagonal terms are there. Okay. So, the 6 independent quantities are there. So, if we are free to choose the orientation of the reference frame, then I can always have some reference frame such that Ixy, Ixz and Iyz they are equal to 0. Okay. And these axes of these reference frames when so aligned, okay, that they make these terms equal to 0, these axes are called principal axes, and the corresponding mass moment of inertia are called the principal moment of inertia. So, next let us see the center of mass. Okay. It is the unique point where the entire mass can be considered concentrated for the translational dynamics. Okay. And mathematically this is how it could be given. Okay. So, this is how mathematically it is defined. Okay. And for uniform shapes, center of mass coincide with the geometric centroid, say for sphere, cylinder or rectangle. And for composite bodies, say a robot link, center of mass of the system is weighted average of individual links center of mass. Okay. Now, let us take an example here in order to find out the inertia tensor, okay, for this one. So, I have rectangular body of uniform density rho, okay, and say this is the coordinate system x, y, z, okay, about which I have to find out these terms, okay, that is the inertia tensor. Okay. So, the volume, elemental volume, this element can be given. If I consider an elemental volume over here, this can be defined like this. So, next I can define I x x, okay. So, this is the elemental mass and this is y square plus z square, and here you see your x varies from here 0 to w. So, this limit, y varies from 0 to L, this is the y. So, we have this limit, and the z varies from 0 to h here. So, we have this limit for the z. Okay. So, initially I carry out integration about x. So, this is what this 0 to integral 0 to w will be giving me the w term, okay, and then I can carry out integration about say y. So, I get this term, and finally integration about z. So, I get this term. Okay. Now, from here if I take h l omega outside, and as rho already we have, so I will get the mass term. So, I have got m by 3 and here L square plus h square. Okay. So, this is for Ixx. So, in case of Ixx, I do not get the parameter in the which is there in the x direction, that is I do not have w here, okay, and I have other two parameters squares being added up. So, based on this logic I can get Iyy, that is m by 3 w square plus h square, and Izz is m by 3 L square plus w square. Okay. Next, let us see how this other that is the cross terms evaluated, that is Ixy. So, it is xy mass of the elemental volume. Okay. So, we can simplify this. So, okay. So, this is what the first integration will be giving us, then the second integration, and finally the third integration. So, this is if I represent mass as rho HLW, I get m by 4 WL. Okay. So, in this case in xy what I get x and y terms only. So, x is w and y term is L. So, I get x and y term. So, for the yz I get y and z term, and for the zx I get z and x term, which is h and w. Okay. So, this way I can complete the inertia tensor, this one which is a 3 by 3 matrix. Okay. So, the inertia tensor is a function of the location and orientation of the reference frame. I already talked about that. Okay. So, in deep learning for robotics, the inertia tensors appears as a structured matrix. Physics informed networks encodes its symmetry and positive definiteness as hard constraints. So, these things we are going to see further when we will be discussing the AI related part of this course. Okay. Next, let us see the parallel axis theorem. Okay. The parallel axis theorem, as I said, its role is to evaluate the moment of inertia about an axis which is parallel to the axis passing through the center of mass. Okay. So, it computes the inertia tensor under translation of the reference coordinate system. Okay. So, the parallel axis theorem relates the inertia tensor in frame C with origin at the center of mass to the inertia tensor with respect to another arbitrarily translated reference frame. Okay. So, say Izz about A will be Izz about center of mass, which is C, plus m xc square plus yc square. Similarly, Ixy about A is equal to Ixy about C minus m xc yc. Okay, where this xc yc zc is the location of the center of mass relative to A. Okay, and this could be, the theorem may be stated in a vector matrix form by this relationship. Okay. Those who are interested, you can write the component form this equation and try to derive these two equations from this equation. Okay, that you can do. It's a small exercise for you. Okay, so robot links rotate about joint axis, not their own center of mass. So we use this concept to evaluate the inertias about the joint axis. Okay, so parallel axis theorem is applied repeatedly to compute the effective inertia seen at each joint motor, because our joint motors are going to be placed at the joints. Okay. So, this is another simple example which we can use here. In the previous example, we have already evaluated inertia tensor with respect to A axis. Okay. So, using parallel axis theorem, we can evaluate the inertia tensor about the frame axis of the frame C. Okay. So, we have xc, yc, zc, this is defined as like this. Okay. So, half of the length, width and height, and then this is the relationship for using parallel axis theorem which we have seen previously. So, I just substitute this value for the izz about A here, this we have evaluated, this one I want to evaluate, and this is the mass and these values I have put in. Okay. So, from here I get this value m by 12 w square plus l square. Okay. Likewise, I can write this for this equation. Okay. And here this value is minus m by 4 WL, this I have to evaluate, and this is m, I can write xc yc value as this one. So, we see that this term is 0. Okay. So, resulting inertia tensor matrix is this one. Alright. So, here you can see that the off diagonal terms are 0 here. It means that these axes are the principal axis. Okay. So, the common geometric bodies where the axis is passing through center of mass, these are some of the shape of the bodies which we may use in some form of the robots. These are say solid sphere, any diameter, these are the values. You can get these values in any textbook also, and this is what we have evaluated right now. Okay. Fine. So, mass distribution in robot design, what we have, the distal mass reduction, the aim is to minimize mass far from the base to reduce effective inertia at shoulder joint by say r square factor, and this enables a smaller and the cheaper motor. Then the center of mass placement, strategic placement of batteries, actuator and counterweight keep the system center of mass stable across all the configuration, especially if I am talking about say your mobile legged robots and so on, there this is a prime importance. Okay. Then the link shape optimization, we do not want links to be the heavy, otherwise our actuators are going to be of a higher capacity, bigger gear motors and all. So, hollow tube, I-beam and lattice structure reduce mass while maintaining stiffness. So, AI driven topology optimization can automate this aspect. Then balanced design, we need to have the symmetric mass distribution about robot rotation axis, reduces the product of inertia. So, the control equations are going to be simpler. Then inertia matching, that is the motor inertia is approximately equal to load inertia, maximizes power transfer efficiency, and AI tunes gear ratio to match this condition, and less distal mass means faster motion. Okay. And more proximal mass, that is the better stability. AI learns optimal trade-off per task. Some additional facts about inertia tensor, if you look at, if two axes of the reference frames form a plane of symmetry naturally, so for the mass distribution of the body, the product of inertia having as an index the coordinate that is normal to the plane of symmetry, that is going to be 0. Alright. So, if we have something like this with the x and y here, so any index where your z is coming, the inertia corresponding to that cross term is going to be 0. Moment of inertia must always be positive and product of inertia may be positive or negative. Okay. The sum of the three moment of inertia is invariant under orientation change in the reference frame. The eigenvalues of any inertia tensor are the principal moments of the body. The associated eigenvector gives the principal axis. I wanted initially to give a small exercise on this, but due to the limitation of time, I am leaving this as an exercise for you. Okay? And practically, the moment of inertia is measured rather than calculated. We have seen so much calculation about moment of inertia, but if you look at the links of a robot arm, they are not of uniform shape. Okay? So, the best way to calculate the moment of inertia of those is evaluating experimentally. Okay, say with the help of an inertia pendulum. So, and this is how we can specify the mass and inertia for AI, okay, in the URDF format, okay, the one which you use for the simulation in the ROS. Okay. So, we can define the mass, we can define the origin x, y, z here, we can have the mass here, okay, and then I can give the principal moments of inertia ixx, iyy and izz. Okay, and the product of inertia terms 0. So, this way I can define in the URDF format. Okay. If you are using SolidWorks, then you have the URDF plugin. From there you can export it directly from the CAD geometry. Okay. So, to summarize, this is our general expression for the linear acceleration of a vector, okay, in a frame. The frame in which that vector is there, that frame may also have rotation as well as translation with respect to some other frame. Okay. Then we have seen the angular acceleration expression, we have seen the parallel axis theorem which we use for the evaluating the moment of inertia, okay, at the parallel axis, and this is the inertia tensor which specifies the distribution of the mass in a rigid body. So, these are very important concepts and we are going to use this concept when we are going to discuss the dynamics of a manipulator. Okay. And so, these are the two references which you can have a look at it, and with this I would like to close for today. Thank you.